Okay, next, let's talk about the software testing foundations. Okay, there's a word by Dijkstra saying that program testing can be used to show the presence of bugs, but never to show their absence. What does this quote mean? So let's digest it. We do program testing or software testing by giving test inputs, and then we check whether there are any software failures or not. Dijkstra said that when we do software testing and we found the failures, we can say that the software has bugs. But if the software that are being tested doesn't show any failures at all, we cannot conclude that the software is having no bugs. Okay, so that's what it means. We can only show that the bug exists by doing testing and found the bugs, but we can never guarantee that the software is without any bugs. All right, so software is just like any engineering products. It can get very big, it can get very complicated, and it is very difficult to guarantee that everything is 100% correctly built. Just like a bridge, like the Golden Gate Bridge here. The engineer cannot 100% guarantee that every single detail of the bridge is correct. So every nut and bolts are correct, they cannot guarantee that. Similarly, a car, which consists of many parts, the engineers also cannot guarantee that the cars are 100% correct. Even every single car is tested before it came out of the factory, it still have some defects, right? So if you want to show that the software is correct, we need to select the behavior and we see whether that behavior is acceptable within consideration of a large number of factors. So we may not be able to guarantee that it is 100% correct, but we make sure that it is good enough according to several factors such as reliability, safety, maintainability, security, efficiency, so on and so on. So how does physical engineers do this kind of checking? So if they cannot prove or guarantee that 100% of their construction are correct, how would they deal with the issue? They use abstractions. So when they build a bridge, they would have some mathematical models that they use to represent the bridge, right? So let's say if you have a suspension bridge like this, they would have this mathematical model to represent the structure of the bridge and how it should be constructed, so on and so on. So by having this kind of abstraction, they can test the model at that level to make sure that everything is correct and it can be built without collapsing. So for software, we have something similar. It's called model-driven test design, which means we're gonna break the test into several small tasks that help simplifying the test generation. And we select different models. So the model will represent the higher level of abstraction of the software. And we use that model similar to using mathematical engineering structure. We design the test values and then we use it to test the software. All right. So in this software testing area, when we say testing, it would mean we want to evaluate the software by observing from its execution. So you must execute the software and then you observe what happens. If you get a test failure, that means the test that you are doing results in a software failure. So when you do some tests, you give some test input and the software fails. That's called a test failure. If everything goes smoothly, you got a test pass or test success, okay? And debugging is the process that you use to find a fault given a failure. So after you have found the test failure, you start doing the debugging process. And then by the failure that you observe, you look for the root cause, which is the fault. Okay. So as I already told in the previous few modules, if you have given a fault, it might not trigger, that fault might not trigger, and it might not lead to failure. So sometimes it is very difficult to relate between the failure back to the fault. Okay, so this is the skills that you have to develop as well, the debugging skills. So in software testing, we have one model. Called RIPR model. Okay, RIPR stands for reach, infects, propagates, and reveals. Okay, what does it mean? You have a test. Okay, you have a test case. You want that test case to go to the location that are faulty location or the location that has fault in your software. So if you have a test, first we will try some method to help the test input to reach the location of the faulty location in your software. And then we want that faulty location to be triggered, and then it infects the software to lead it to the incorrect program states. Okay, so this is called errors, as we already discussed, right? So if the software is in an incorrect internal state, that is software having errors. And human or the software tester might not see the error here because it is inside the software. So we want that error to propagate or being passed on into the final program state and output. So if the incorrect program state propagate here, you would get some part of the program state or output that contains incorrect final state. And there are some parts that are observed by the software tester. And we hope that the software tester will be revealed to the actual failure. So he or she can spot the failure that occurs in the final state of the software. So that summarizes this RIPR model. When we create test cases, we have many methods to do, but the method that we chose are different in terms of effectiveness on reveal or reach, infects, propagates, and reveal. Okay, which we're gonna keep discussing each of the methods in the following modules. So the last part in this module, I want to talk about the activities of the test engineer. Okay, so a test engineer is an IT professional, and he or she is in charge of one or more test activities, including designing test inputs, producing test case value, running test script, analyzing the results, reporting the result to the developers and the managers. So these are the tasks of the test engineers. But usually everybody in the software development sometimes will wear a hat of a test engineer. So if you are a programmer, you need to write unit tests so that at that part you will become a test engineer. So each software artifact should have some associated test cases. Either it's going to be unit tests, it's going to be integration tests or system tests. And the people who define the test case usually will be the one that creates such artifacts. So if the programmer write the method, he or she should be the one that write the test for it. And the bigger role is called the test manager. So the test manager is the one that in charge of the whole team. So let's say he is the leader of the team of test engineers. And he is the one setting the test policy and the process and interact with other managers and also help the test engineer to finish their work smoothly. So it would work like this. You have first test engineer who design the test cases, and then the test case is created as an executable test. Okay, so the first part will be just designing the test cases, and then you turn it into the actual executable test. And another test engineer will put that test into a computer, giving the program that you want to test, and then you would get the test output. And another test engineer, so this is the second test engineer, and the third one, or maybe he or she is the same person, look at the result and then evaluate whether the test is good enough. And the test managers are the one that overseeing the whole process here and taking care of the whole team. Okay, to summarize, in this module, we discussed the discipline of test analysis and testing that can be divided into 6 main principles: sensitivity, redundancy, restriction, partition, visibility, and feedback. And we discussed the model-driven test design, the RIPR model, and the activity of the test engineer. So that's all for the module, and see you in the next module.